Hi, my name is John Paul Raj and I'm on a mission to make the learning of math fun. So if you're new to this channel, please do consider subscribing. On this particular video, I'm going to solve the IGCSE 0607 paper 6 from October-November 2021. Let's start. As mentioned in the introduction, this is the paper 6 for IGCSE 0607 International Mathematics. In this particular video, we're going to solve the investigation part only, and this is from October-November 2021. All right, let's start. This is entitled Pythagorean sets of 4, and you need to read everything, okay, even the description of the investigation. This investigation looks at finding the integer lengths of the sides of a cuboid that has an integer length for its diagonal. So they have given an image, okay, that's a cuboid PS. That's the diagonal of the cuboid they're referring to. And this particular cuboid has dimensions PQ is 3, QR is 5, and SR is 6. The diagram shows a cuboid with sides of length 3, 5, and 6, integer lengths, okay? Using Pythagoras theorem in triangle PQR, this is on the base, okay? The base is a rectangle. So PQR is a right angle triangle on the base with the diagonal PR, the diagonal of the rectangle, the base rectangle. Using Pythagoras theorem in that triangle PQR gives PR square is equal to 3 square plus 5 square. Find the value of PR square. That should be pretty straightforward. So we can say PR square is 9 plus 25, which is just 34. All right. They've not given any units, but be very careful. This is PR square, not PR. Okay. Just leave it at 34. Using Pythagoras theorem in the triangle PRS. This is part B. PRS. PRS is that other triangle. That's also a right angle triangle, by the way. And that PS is the diagonal of the cuboid, which is also the hypotenuse for this particular triangle PRS. Okay. So they're saying using Pythagoras' theorem for that triangle PRS gives you PS square. That diagonal square is equal to PR square, which we just found in part A, plus 6 square. And that is also pretty straightforward. So we can write PS square as PR square is 34 and 6 square is 36, which should give us 70. Again, we can just leave it without writing any units because it's PS square. Okay, question number 2. This is another cuboid, and this time they have generalized A, B, C, and D. The diagram shows a cuboid with sides of integer length. Remember, they are emphasizing integer length. So A, B, C are integers apparently. Its diagonal PS has integer length D. So all A, B, C, D, they are all integers. Use Pythagoras' theorem in triangle PQR. PQR again, it's a similar idea to the approach in question number 1. So we can say that it says to write down the expression for PR square in terms of A and B. So PR square is equal to A square plus B square. Pretty much very similar to what we did in question number 1A. All right, 2B. Use your answer to part A and Pythagoras' theorem in the triangle PRS. Very similar to question number 1, as you can see. So we can say that in triangle PRS, that's a right angle triangle. So PS square should be equal to PR square, which we just found in part A, just like in question number 1, PR square plus the SR square. SR square, I believe, is C. So PR square is A square plus B square, and SR square, SR is C, as I said, is C square, okay? And PS is labeled as D, so we can just say, therefore, D square is equal to A square plus B square plus C square. I know it looks like a lot for 1, okay, just for 1 point, but be as specific as possible in your answers, like writing of answers. Because this paper, as I said before in some of my earlier videos, paper 6 is all about communication. There are points specifically assigned for how you communicate your answers, okay? Not just this 1 point, okay? A cuboid has sides of length A, B, and C, where A, B, and C are integers, and A is less than or equal to B is less than or equal to C. If the length of the cuboid, if the length of the diagonal D is also an integer, then A, B, C, D, okay? That group, that set A, B, C, D is a Pythagorean set of 4. Okay, so what we have seen in question number 1 and 2 is just laying it out for this idea called the Pythagorean set of 4 integers where A, B, C are the sides of the diagonal and the D is also an integer. A, B, C are integers and sides of the cuboid, and the d, the diagonal of the cuboid, is also an integer. So that set ABCD is a Pythagorean set of 4. Use d squared is equal to a squared plus b squared plus c squared to show that a cuboid with sides of length 4, 17, and 28 give a Pythagorean set of 4. Complete the Pythagorean set of 4. All right, so they've said that the sides are 4, 17, and 28. So we just need to find out the square, right? So basically d square, the diagonal square, is going to be equal to 4 square plus 17 square plus a 28 square, okay? And then we can just quickly jump onto a calculator, all right? And let me just show that quickly, all right? So here we go. Can you see my calculator? I can just add the calculator page, and that's just 4 square. Yes, I know we can do all these things without the calculator also, but because the calculator is allowed, why don't we just make use of it, right? So 28 square is, this is set to, what is it set? Is it set to approximate? Always make sure that your calculator is set to, well, exact is good. Just leaving it at exact is good. But sometimes, if you're doing some questions, then you need it in approximate also. But you need to know where to come to, which particular option you need to come to change that setting. So it's not that, just one setting is always reserved. Especially in paper 6, you may need to switch between, as in this case, approximate and exact, okay? Hit enter, and that's 1089. But we're looking for the square root of that number, aren't we? So the square root of the previous term gives you 33, all right? So I switch back to my pad and say that is a 33. So d square is, what's that? 1089, giving you d is the square root of 1089 as 33. And then you can fill in the blank here, okay? Show all you're working as much as possible. Question number 4. In a Pythagorean set of a, b, c, d, d squared is equal to a squared plus b squared plus c squared. All right, they repeated this many times. When d is equal to a plus c, show that ac is equal to b squared over 2. All right, so when d is equal to a plus c, d is the fourth integer in that set, okay? A, b, c, d. D is equal to a plus c. So we know this relationship, right? So we can say d square is equal to a square plus b square plus a c square, and d is equal to a plus c. So you have a plus c, the whole square, is equal to a square plus b square plus c square. And then when you expand this term, on the left-hand side, you should get a square plus 2ac plus a c square should be equal to a square plus b square plus a c square. And clearly you can see that the a square, the c square will just cancel off, which gives us just 2ac is equal to b square. And that should reduce to ac is equal to b square over 2, which is what we were supposed to show. Clear? Part B is then asking us to explain why B must be even. Why B, the second term, the second integer in that Pythagorean set of 4, why it must be even. Well, when you look at this answer, AC is equal to B square over 2. We know that that's going to be an integer. Why? Because, each of them, A, B, C, D, they are all integers, right? Because in this Pythagorean set of 4, we are already told that they must be integers. A, B, C are integer lengths of the cuboid. The diagonal D is also an integer length, and that's when we say that it's a Pythagorean set of 4. So if A and C are integers, I'll write it that way, okay? Since A and C are integers, their product, AC, is also an integer. Right? The product of two integers is going to be an integer, all right? That means b squared over 2 is an integer. How did we come to that conclusion? Well, because AC is equal to b squared by 2 from the earlier answer from part A, we know that AC is equal to b squared by 2. A and C being integers, the product AC is an integer, giving us b squared over 2 is an integer. And if this is an integer, it clearly means that b square must be even. Why is b square even? Because b square by 2 is an integer, all right? That means it's clearly divisible by 2, all right? So, b square is clearly divisible by 2. That means b square must be even. And if b square is even, then b is also even. This comes from the idea that the square of every even number is also even, okay? So that's how we used it the other way around, that if the square is even, then the square root is also even, okay? That's the reverse idea we've used. The square of every even number is also going to be even. So how did we do this? We started by saying that a and c are integers because they form that, they are members of that Pythagorean set of 4, they're integers. So their product is an integer. A times c is an integer. If a times c is an integer, then b squared by 2, which we just proved earlier in part a times c is equal to b squared by 2. You know, they're equal. So that means b squared by 2 is an integer. If b squared by 2 is an integer, that term b squared by 2 is an integer, then b squared must be even, right? Because it shows that b squared by 2 is an integer. That means it must be divisible by 2, which means b squared is an integer. And then because b squared must be even, it follows that b must also be even. Okay, let's move on to question number 5. Here is a method for finding Pythagorean sets of 4 using question 4. Well, okay. Question 4 is what we just did here, using this method, using some method that's specified here. There's a method that's given. Choose any even integer for b. Any even integer. Calculate AC using question 4a. What happened? Okay, b squared by 2. So we just choose an even integer and square it and divide by 2. You'll get a times c, right? That's what they say by saying calculate AC using question 4a. Find all possible pairs of integers for a and c where a is less than c, okay? And they are integers, by the way. A and c are also integers. Use this method to find all Pythagorean sets of 4 when you choose b is equal to 8. Remember, we're starting with b and an even integer, okay? B is 8. So let's do that, okay? So b is equal to 8. When b is equal to 8, b squared must be 64. Which means b squared over 2 is 32. Is that right? And that b squared over 2 is 32 is going to be equal to a times c. A times c, all right, from the previous. So that means AC is 32. Okay, and we need to find all possible pairs of integers for a and c with a less than c. So let's just find out different factors of 32. 32, I will write 32 as, we can write 32 as 1 times 32. Okay, so 1 and 32. Let's just write it at 1 times 32 is 32. We can say 2 times 16 is 32. All right, 3 is not going to go. We can say 4 times 8 is 32. And in all of these cases, we can see this is less than that. So if we take a as 1, then c is 32. If you take a as 2, then c is 16. And if you take a as 4, then c must be 8. Of course, you can have even the other factors, right? 32 times 1 and 16 times 2, but they're saying a must be less than c. Use this method to find all Pythagorean sets of 4. Okay, so we need to find the sets of 4. So when a is 1, b is 8, so one set. So you can say, write down the Pythagorean sets of 4 are as follows. The first one, if a is 1, b is set as 8, c is 32, and we know from question 4 that d is equal to a plus c. Okay, that's how we have used this. AC is equal to b squared over 2, right? D is equal to a plus c. So the d should be so it should be 33. That's one set. The other set can be 2 and b is still 8. C is 16 and a plus c is going to be 18. Clear? And the third set is 4. A is 4, b is 8, c is also 8, and d must be 12. All right? Those are all the possible Pythagorean sets of 4 from these values. For b is equal to 8. Okay, moving on to the next question, number 6. Which one of these two sets is a Pythagorean set of 4? Okay, which one means there are two sets given and one of them clearly is not a Pythagorean set apparently. And we have asked to show how you decide, right? So both of them has the first three the same, 18, 24, 72, 18, 24, 72, ABC are the same. It's just the D that's different. One is 78, one is 84. Now in the earlier parts, we had A plus C is equal to D. And if you can clearly see A plus C, 18 and 72, they do not add up to 78 or 84, okay? And the reason we cannot use the technique D is equal to A plus C is because B square must be equal to AC. Okay, B square is 20, B is 24 here and clearly 24 square. Let me just check that quickly on my calculator. Okay, where is my calculator? 24 square, let's just see that. B square is 576 and then 18 times 72. What is 18 times 72? 18 times 72 is clearly not equal to B square, and because of that idea B square is not equal to A times C, we cannot use that idea of A plus C is equal to D. I hope that is clear, okay? Because the assumption made in part 4, the question 4 was D is equal to A plus C, which we used in question number 5 to generate or obtain these sets of 4, the Pythagorean sets of 4. A plus C was equal to D. The reason we use that idea is because those are related. When D is equal to A plus C, AC is equal to B square over 2. So that's why that idea cannot be used in 6. But what can be used for 6 is the fact that, remember, these are integer lengths of a cuboid and integer diagonals. So we can check that way that the original idea of A, B, C, D, the original idea that we had, that D square is equal to A square plus B square plus C square. So we can use that idea. D square must be equal to A square plus B square plus C square. So let's check that, okay? So D square, 78 square. Let's jump back to the calculator, all right? And here we have, what's 78 square? 78 square happens to be 6084. And let me just do the other one also, 84 square. The other D was 84. 84 square, 7056. Now let's check A square plus B square plus C square, which is 18 square plus a 24 square and a 72 square. Okay, and we're getting it as 6084. So it is the one with 78. Is it the first one? Cool. Let's come back to the iPad and say that this is how we've decided. Okay, so we say that 78 square is equal to, what was that? 6084. Okay, and A square plus an 18 square plus 24 square plus 72 square is equal to 6084, which is 78 square. Okay, if you want, you can even write down that 84 square is equal to 7056. Okay, and that's the one that we reject. Okay, so this one is the one that we reject, and we can write down the answer to the fourth term. The D for this set, Pythagorean set of 4, is 78. Okay, moving on to part B of 6, question 6. K times A, K times B, K times C, K times D, Ka, Kb, Kc, Kd is a Pythagorean set of 4 where K is a positive integer greater than 1. Okay. Use algebra to show that ABCD must also be a Pythagorean set of 4. I think that's very simple, right? Because if it's a Pythagorean set of 4, then Kd square, the whole square, okay, must be equal to Ka, the whole square, Kb, the whole square, Kc, the whole square. Clear? Because it's a Pythagorean set of 4, all right? And if you want, you can write down since Ka, Kb, Kc, Kd is a Pythagorean set. Can you guys see what I'm writing? Of 4. Clear? Once you have this established, then you can just say, all right, that must be then K square D square is equal to K square A square plus K square B square plus K square C square. And then we can factor out K square A square, B square, C square, and you have a K square D square. Divide K square on both sides, okay? It'll cancel out nicely. to give you d square is equal to a square plus b square plus c square. All right. So this means a, b, c, d is a Pythagorean set of 4. All right, moving on to part C of question 6. ABCD is a basic Pythagorean set of 4. Okay, notice that italicized word basic. ABCD is a basic Pythagorean set of 4 if the numbers A, B, C, and D have no common factor other than 1. Okay, so that's the basic idea, because KA, KB, KC, KD, the common factor is K. All right, and so they're asking us to find the basic Pythagorean set of 4 for the answer found in part A. Part A is 16, 24, 72, and 78. Okay, so let's just write that thing down. 18, 24, 72, and 78. And it means that, what's the common factor here? What's the common factor? 6. 6 times 3. All right, so you can write this thing as this is 6 times 3. This is 6 times 4. This is 6 times 12. Yep, and this is 6 times 13, I believe. Okay, which means basic, I can write down, which means 3, 4, 12, 13 is a basic Pythagorean set of 4. Okay, all right. Number 7, is this the last one? Great, hooray. Okay, the method in question 5 to find Pythagorean sets of 4 is, okay, they've summarized the method in question number 5, okay. What's going on here? Choose any even integer for B, calculate AC using question 4a, okay, that was the same idea, b square over 2, right? B square over 2, what was that? Yeah, b square over 2 was AC, clear? That's 4a, where are we? Okay. Find all possible pairs of integers for A and C where A is less than C. All right, the same way, the products, okay, as we did. Use this method to find 2 basic Pythagorean sets of 4 where the smallest integer A is 2. So they've already said you have to fix 2. They've not given us any B. All right, so we can choose our B. They already had done for B is equal to 8, I think, in that particular question, right? In that particular question, it was B is equal to 8, if I'm not mistaken. Yeah. So let's just take something else. Let's take B is equal to 6, perhaps. Okay, so let's just choose an even integer. Let's say when B is 6, and we'll ask to find basic, okay, basic Pythagorean sets of 4. That means, there's no common multiple for all the 4 terms. B square must be 36. B square over 2 must be 18. And AC is 18, right? Now we look at all multiples for A and C, given that A is 2, all right? So when A is that, if AC must be 18, then let A be 2. That means C must be 9, right? Because A times C must be 18, okay? A and C are found out, and we are given the same idea of D will work. Okay, A plus C will be equal to D. So the set has to be 2. Therefore, 2. B is 6 and C is 9. A plus C is 11. So there's nothing common. There's no common factor for all these 4 integers, 2, 6, 9, 11. That's a basic Pythagorean set of 4. And we need to find 2 such, okay? Using this method, the question said to find 2 such. So let's do that also quickly. Just draw a line here, okay? So B is equal to 6. Let's do one for B equals 10. Okay, we need an even integer, right? So when B is equal to 10, the same way, okay, B square is going to be equal to 100. B square over 2 would be a 50. That means A times C will be 50. And we need A to be 2. Remember, that's what they said. The smallest integer A must be 2. So when let A be 2, C must be 25, right? Because A times C is 50. So what do we have the Pythagorean set of 4 as? So it's 2. Our B is 10 this time. Our C is 25, and 25 plus 2 is 27. And clearly there is there's no common factor for all those 4 integers. This is going to be is a basic Pythagorean set of 4. Clear? So that completes the investigation part, and the modeling part we will see in the next video. I hope you have understood the questions and the reasoning. It was pretty straightforward. There was not much of a calculator option or something. And I think that this is the simplest investigation I've found in any of the paper 6 questions that I've solved. Okay, if you found this video helpful, please make sure that you like, share, and subscribe to this channel. I'm going to see you all in the next video.